right, guys. So for today's one, you don't have to write anything. Sometimes you write something. I'm going to give you a sheet of paper, but for today, it's pretty chill. The theme of today is functions. So what I'm going to do, we're going to play a little game. Okay. I'm going to ask you to give me a number. And then I'm going to do something to that number and spit it back out. The game is, what am I doing? Okay. So what function am I? Think of it like that. So someone give me a number.
7.
7. Okay. 50.
25.
What is it?
25.
25. 51. 51. Let's see. Well, let's see. Give me another number. Huh?
3.
3. 7.
Yep.
I'll keep going.
2.
2. 5. 12. 25. 6. 13. Okay. So what do you guys think I'm doing in my head?
Double it plus 1.
Say it again.
Double it plus 1.
I'm doubling it. Whatever you tell me, I'm doubling it and then just adding 1 to it, or timesing it by 2 and adding 1 to it. Okay. Sweet. So that's the essence of a function. Okay, is the number that you told me, we're going to call that an input. My head does something to that number, some operation, and then the number I spit back, that's what's called an output. Okay, good. So let's see, let's formalize all this. So section 3.1 to 3.2 called an introduction to function. I was trying to do something crazy, but I was like, you know what? I don't know if I could do it that fast in my head. So I kept it chill. All right, guys. So let's start with the definition that we're going to be using for what a function is. We're going to say a function is a rule that assigns to each element, it's very formal, okay, the definition, to each element from a set called the domain, so it's a rule that assigns to each element from a set called the domain. That element, for example, is like the number that you were telling me. Exactly one element in another set called the range. And I'm just going to highlight like very important parts of the definition. And so the thing I was doing in my head, that's the rule. That's what you guys had to figure out. What was the rule that I was doing? You guys noticed that the rule was I double it and I added 1. The number that you were telling me, that's the element. And we'll talk about what the domain is. Now, would have been really confusing if you guys gave me a number and I gave you guys 2 different numbers. That would have been really hard to do, right? So a very essential part of the definition is that whatever the output will be, it'll be exactly one output only. Okay? And so visually, most of the time, we're going to be using X values to be our input values. Then you're going to grab a particular X value and you're going to plug it in to this rule. The textbook shows it kind of like this little computer, like a little machine that inputs things and outputs. Right? So the rule is the function. That's what we're going to label F. It tells you what to do to your input. And so that was my head doing something to the number you gave me, and then I spit out a number here. That's called the output, F of A. And in general, we're going to let those be the Y values. on a vertical axis. And the X values are gonna come from a horizontal axis. And so this is where the domain is going to come from. These input values, these input values are going to come from our domain. So that's our inputs. And our outputs are going to live in the set called a range. So the range will contain all the outputs of the function. Kind of, so that's like a visual of what this definition is saying. Okay. And only one thing can be spit out, not multiple things. Okay. And this rule, which is the function, can be expressed in 4 different ways. It can be expressed algebraically, verbally, kind of like the way you guys told me, you double it and add 1. With a table, or graphically. Okay. If you're going to like, let's say, like economics, like more finance route, you're going to see a lot of tables. And so the functions, the rules are going to be represented more in this format. Okay. If you're doing like statistics, probability, all that stuff, you're going to see a lot of graphs. And then if you're doing more like in the I guess like physics, more than the engineering route, you're going to see a lot of functions, a lot of formulas. So let me show you guys some examples. You guys can see. So let's do example 1 is an algebraic one. Let's do the one from the warm-up. What was the rule? What was the rule? What was I doing to the number? You're doing 2x plus 1, right? Or you're already calling the number x, right? It's okay, it's okay. So the way we write it is we say x is what we're going to input, and the outputs, they're going to be represented by the expression 2x plus 1. Whatever that number is, you double it, add 1 to it, and that's what the output will equal. Leave some room here. Number 2, let's do one that's verbal. These are the more uncomfortable ones because they're in the word problems. Okay, so part of the challenge of word problems is translating verbal to an algebraic expression. So let's say you're reading something and it says, the total price is the cost of purchasing X $10 items plus an additional fee of $5. And so it's a mouthful. Okay, I'll slow down. Shift recording, yeah. And so here it's being described in terms of words, the relationship with these things. And so part of the challenge of a word problem is how can I translate a verbal function into an algebraic function? Okay. All right, let's see, leave some room under here. Let's do number 3. Let's do one that's a table. This one I see a lot. Let's do a table where it's your DVC student. Let's just make it up. And the student ID. Don't give me your actual student ID, okay? I'll just say, let's say there's a student named Sam, and I'm just gonna make it up. 1356182. Okay. And then so on, whatever these are. When you look at a table, you want to be very careful because table can just have random data. Okay. So when you guys are looking at a table, you want to make sure you really focus on the green part, that it has exactly one element. So for example, if you're looking at this table, what would you want to call the inputs? The student. So you pick that. You say, okay, if the DVC student is the input, then according to that definition, that student should only correspond to one student ID. It can't correspond to multiple student IDs. Okay, is that true? Oh God, I hope so, right? So yes, this would describe a function. Okay. And so yes, when you guys are going to look at tables on the homework, you want to be very careful that you are talking about a function. Okay. Okay, let's see, and then let's do graphically. I'm going to draw two of these for you. Let's do two. We're going to do two of them. Put 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5. And then do 5 on the vertical. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And we're going to label the horizontal values. We're going to say this starts at 1995. And then 2000, 2005, 2010, 2015. And the same thing with the other one. 1995, 2000, 2005, 2010, 2015. Let's see if this guy's alive. Nope. Okay. For the first one, we're just going to do points. So put the point about right here. Oops, I forgot to label the vertical ones. Sorry. Let's just go by tens. 10, 20, 30, 40, 50. 10, 20, 30, 40, 50. Okay, so we have a point about above 1995, very close to 10. 2000, let's put 20. 2005, let's put about like 25, like halfway. 2010, let's put 35, about halfway. 2015, let's put 50. That. And that's the graph, it's just points. Okay, whatever this represents. Well, usually the problem will give you the units and the content here, context. The second one includes the same points that the other one does. 25, 35, 50. But this one connects them like this. Like that. Okay, so one has them connected. One does not have them connected. Let's go back to this the green description here. Okay. If we call the years the input values, the output values here will be these values here. Okay, the vertical ones. So is it true that for each year, it corresponds only to one value, one of these values? Yes, right? Versus if I had a different dot here above 2015, now I have 2015, but it's corresponding, it's outputting two values. In that case, this would not represent a function. Right? That would not represent a function. But in this case, it does. Okay. What about when I connected all the dots? Is it true that now, see the difference between here and here is that in this scenario, what are the input values that we're using?
Fixed 5-year intervals.
Well, that's the question that's where I'm about to get. Are the inputs only these 5 years, or is it all the years between 1995 to 2015? Only these years. Versus here, I'm considering the also points in between, right? So I am considering input values that are in between 1995 and 2015 only. But in this case, it's all those years. Okay. Is it true that for all those years, they only correspond to one of these numerical values?
Yes.
Yes. If the curve went like this, notice that now for like, let's say this year, 2013, it corresponds to one value here, but it also corresponds to a different value here, because now there would be 2 points associated to that year. So then it would not be a function. So that's why I was telling you, this is very important for it to be a function. So we're going to learn how to determine that in different ways. Okay. Okay. With someone next to you, the folks that are usually next to you here, I want you guys to try your best to describe what the domain and the range would be. I'll do the first one with you. How about that? And then I'll let you guys take these ones. Okay. So let's see. So domain and range. Okay. For this function, the x were the numbers that you were telling me, right? You guys were only giving me whole numbers. Could you have also given me negative numbers? You could have also given me negative numbers. I would have doubled them and added 1. Could you have given me like decimal values of 2.5 and pi and all that? Yes. So what's the smallest number that you can give me? There is none, right? So how were we writing that for Monday's class? We were saying that it goes negative infinity because there is no smallest number. So we wrote negative infinity, always put parentheses with infinities. Is there a biggest number that you can give me? No. So then we put positive infinity to go like that. So you would include all the values in the on the x-axis. You would include all those numerical values. Those could be plugged into the function. When the range is always a little harder, okay? When you give me one of these numbers, whatever it is, and I spit out a number, is there a smallest number I could have spit out, or could I also just go up to negative? Like if you give me negative 1 million, I would have doubled that and added 1. That would have still been a very big negative number, right? So there is no smallest negative that I could have given you. So it's again, negative infinity. Is there a biggest number I would have repeated out to you? No, right? So then it goes, there is no upper bound, so it goes all the way to infinity. Okay. Okay, I'm gonna have you guys try these on your own, since I'm talking too much. So with someone next to you, I want you guys to try to determine, first try to do it in words, and then see how you would write it down with notation. With your classmates, try to discuss what the domain and ranges look like for these 4 different functions. Here, do it for these 2. Domain, range, domain, range. All right. Let's see, can I have you join here since I have a camera there? Let's see, I have YouTube. I'll have, let's see what I want you to do. Air. Air. And then I get triple. Yeah, and then I'll have you guys just kind of pump up here. The person next to you. And here, pair up to the person to the side of you. Pair up here, and I'll have you guys.
It's a free for all these things.
I don't know, what's the guy? You guys. Okay. I could feel like the next. I think the domain range is to be flying. No minimum. But I don't know. Yeah, that's true, but like. The draft sounds so good, right? And that's what I always say. That's all I do, and I'm not sure. It's just like. Draft and something like that, yeah. But in that case, I'm not sure.
These are just numbers, right? Yeah. Sometimes.
I have no idea. There's only 5 exit.
Well, like.
But you can see like. 1997.
So,
Yeah. But then the output, like,
they all questions, yeah.
Well, I don't know, that's.
Yeah.
So in this case, like we were saying, only these 5 years, right? That's it. So you wouldn't use an interval, because interval includes everything in between. So in this case, you would write it as a list. You write it as 1995, comma, 2000, comma. Yeah. And so that's something you guys are gonna wanna do when you're looking at your functions. Is it like continuous numbers that include everything between? Or is it like more discrete things? And so in this case, you wouldn't use the interval. Yeah.
What's that?
It depends on the notation, and that's what I'm about to talk about. Yeah.
But I think both of them. When I took the first, I did it. No, but I did.
All right, class, let's see, I am getting a lot of questions about these two. So let's see real fast. Let's take a look. So I think, let's go with, let me go with this one first, and then we'll finish up with that, okay? For the domain, I guess, what were you guys thinking of being the input here? What were you referring to the input? The number of items?
Yeah.
Okay, so then if that's your domain, what would be the small, is there a smallest
Yeah.
number of items?
0.
It would be 0.
But then why would you pay the additional fee?
$5. The government just wants you.
That's just-
Into the story.
Yeah, yeah. But here's where you gotta be careful.
Yeah.
So can you include, can the domain include the number 0.2?
No.
Because you can't have 0.2 items, right? So in this case, you will not be using an interval. Because interval includes all the numbers in between one another. But here, it's 0, what's the next input? 1, but you're not including anything in between that, right? And then the next input is 2. So in this case, you have to express the domain in what's called a set notation as a list. And so it will look like this. You do a set bracket, and then you write 0, 1, 2, 3, and then it's a big infinite list. And then you close it with a set, that's called the set bracket here. And yes, you can write more than 2 numbers. Versus in interval notation, you only write the lower bound and the upper bound. Okay? So these are called set brackets. Brackets used for lists. When your domain and range is a list of things. Okay, range. What do you guys think was the output of this function? What was it spitting out? The amount of the cost, right? The total price. So is there a smallest price?
$5.
5 is 0 a smallest price?
No.
No, because they still want you to do this damn initial bid, okay? So the lowest is $5. What would be the next one?
15.
Is so $5 is it for 0 items, right?
Yes.
But then for 1 item, it would be $15 because it's $10 plus 5, right? But notice, is the range going to include the numbers between 5 and 15?
No.
No, right? So it's going to be a list again. So it would be 5, comma 15. Then for 2 items, it'll be $20 plus 5, and then 35, and then so on, right? So in this case, I didn't tell you guys this. I wanted you guys to kind of like be like, how do I express this? Is because it is different. You guys use set brackets. Okay. When you use set brackets, if a number shows up multiple times, you don't have to write it multiple times. You just write it that one time. Okay, question, yeah.
This is like an input and like you're doing a computer problem, how would you like write that down?
If you're, what do you mean?
Like, you have to like type out answers, or would these all be like multiple choice? Like if it was like you're doing a on my computer?
Oh, like on WebAssign or something. It would probably be multiple choice. Yeah, because you can't,
Yeah,
that dot is too confusing, yeah. Yeah, good question, good question. Okay, this is the maybe through this discussion, this might help, okay? Maybe, we'll see. Okay. I think you guys said you wanted to call these the inputs when I asked you, right? So then these will be the outputs. And that's important because if these are the inputs, then this is what you use to help you determine the domain. Okay? So what were you guys describing to be the domain? What kind of things are you plugging in? You're plugging in names. So would you use interval notation or set bracket notation? Because it's a huge list of names. It's all your names plus all the other students at DVC. All those names are the domain. So again, it's a big infinite list. What do I put here? Sam. I took a class, so I'm considered a student. And then so on. So it's a huge list of names. Big infinite list of names. Okay. Okay, range are the student IDs. But would that be interval notation or will that be a list? It'll be a list of student IDs, right? But will the number 5 be in that list? No.
Would you would it be like 0000000, however many, like 7 zeros and then 99999?
Yeah, so you need your student ID to always have how many digits? Your student IDs have to have 7 digits, okay? So I think what you're saying is like you would start at 00000, that's 7. 1, 2, 3, 4, 5, 6, 7. And then
9999.
and then all the way up to 9999999. Yeah. 9999999. 1, 2, 3, 4, 5, 6, 7. And usually ... is what math textbooks use for, like, there's an infinite amount that continues a certain pattern. And that's kind of how you want to read those ... okay? I don't know if actually we can use 0000 as a student ID.
00001.
Yeah, I don't know. So assuming if you could use that as a student ID, that'd be crazy. I would want to know which student that is. Then you would start here. But if you can't have all zeros, then yeah, maybe it would start here. It kind of depends. I don't know. I don't know that myself. Yeah, whatever the lowest is. Let's just assume that would be the lowest. Okay. All right. This guy here. Domain are the years. Is it all the years in between, or is it literally just those 5 years? So which notation will we use? Set brackets. And literally you will be listing those 5 years: 1995, 2000, 2005, 2010, 2015. That's it. Those are the only inputs for that function. Those are the only 5 years that have output values here. Okay, range is gonna be a little hard because we got to estimate, but what's the smallest value that we used here?
7 or 9.
Whatever that is. What do you got? Let's agree on it. What do we call it? 9? Okay. So that's the smallest one. Do I include everything from 9 to 50? No, because it's not connected, right? It's only going to be the 9, only going to be the 20, only going to be the 25. And then what did I say? I think I said 35 for that one. And then I think I said 50 for that one. And so you would list only those values as your range. So here's where these graphs are gonna differ. They look kind of similar, but the domain and ranges are hella different. For the domain, is it set bracket, list, or interval? Interval now, because it does include everything in between. Does it include 1995? Yes. So in interval notation, my smallest number is 1995, but do I do a parenthesis or a square bracket? Square bracket because you include it. Okay. What's the biggest year? 2015. Is it included? Yes. Newton. Website might throw something like this at you. Look. It'll put an open dot right there. Okay. If it puts an open dot, that means you include all the years from 1995 up to 2015, but you would not include the year 2015 because it does not have a point associated to it. That's how you would read those dots. So let me stop. Because that's a very important thing for calculus to know that. If it's an open dot, it includes all the years up to 2015, but it's purposely open so that you do not include that year. Okay, if it was closed, what would change for the domain? You put a square bracket here. Okay, but let's leave it open just for the discussion. Range. Are we including all the values from 9 to 50? Yes. Do we include 9? Sorry, question.
Did you say 0 because it's less than or equal to 0?
For the range?
Yeah.
If you started at 0, then on this graph, there needs to be a point that has the y coordinate 0.
Okay.
But there isn't, right? So we wouldn't start from 0. Yeah, good question. What's the smallest y value that we're using? 9. Is it included?
Yes.
Yes. What's the biggest y value we go up to? 50. But is 50 included?
No.
No. So then we're going to do parentheses. Okay. So this is what we were going over this stuff on Monday. It's like, boom, now being used. Okay, there's more I can say, but we'll take a little bit later. Okay, questions on that? Maybe a question that you think someone else might have about the domain range stuff?
So are we gonna be mainly doing domain range like that, how we used to, or are we gonna be doing it with the brackets?
It'll depend on the function.
Okay.
That's why I wanted to show you all these so that you can differentiate. Yeah.
So you were saying that set brackets are used for lists, but
Used
yeah, but then the parenthesis form, what is that called?
interval form,
Interval form, is there a tip for that one? Is it used for
intervals.
like unlimited or so not lists, but
If you don't, let's just say if you don't have a list
Yeah.
used. We'll come across another weird thing if it shows up, but most likely, like, yeah, used if you're not dealing with a list.
okay.
Okay. It's smart. Good.
How do we clarify for this range over here that dot doesn't include decimals?
Well, so normally in a set bracket, you do write out maybe like the first few terms, dot. That way you kind of see the pattern that's happening. Yeah, I just couldn't fit.
Yeah.
Yeah, but yeah, good question. And that concept of dot, it will be used a lot when you get to Calc 2. Yeah, so it's prepping you on how to read all this fancy notation, if you have to get there.
So I guess you could say that intervals are for like as long as it's not set data that you're given.
Yeah, that's right. And usually it's used for real numbers. It's just that, you gotta be careful if it's a list. or not. Yeah. Okay, let's see. Okay, let me just show you these real quick. Okay, so I'm gonna skip that part. Okay. So what I want to do now is I want to look at more of the type of functions you're gonna deal with a lot, especially when you get to a calculus course. To keep talking about notation. Right now, it's a lot of notation that you're trying to understand. Let's go with our good old quadratic looking function. Let's say it's y equals x squared plus 1. And let's say we're being asked to graph it. Okay. So graph this equation. And let's review how to do that. One thing that you guys first learn is to make a table, an XY table, to start representing the function through a table format. Okay? You get a sense of what the function is doing. This is all crooked. Let's call the input variable X and the output variable Y. And so to get a feel for this function, you normally pick some X values, right? So let's pick 0, -1, -2, 1 and 2, kind of like in the center to get a feel for it. So you probably do this in your past math class. Do a little review. And then what do we do to those X values? You plug them in. You plug them into the equation to find what the Y value will be. So I'll do the first one only. So to find this Y value, you plug in -2. And for X, you replace the X with that number. What is -2 to the power of 2? 4, not -4, right? Because it's multiplying -2 times -2. Okay, good. So that's just 4 plus 1, which is 5. So that tells you that this will give you Y value 5. And then you just do that for the other ones. Plug in -1, -1 squared is 1 plus 1, 2. Plug in 0. 0 squared is 0 plus 1 is 1. Plug in 1, 2. Plug in 2. 2 squared is 4 plus 1 is 5 again. And then what did you do with that information?
You're gonna graph it.
You're gonna graph it, right? You took these as points. So you went like this. Let me see where I want to put this. Yeah. You made an XY coordinate axis plane. You call this the X value, that the Y value. And then we wrote some units here. 1, 2, 3, 4, 5. 2, 3. So those were the X values, and then we'll do 1, 2, 3, 4, 5. And then, as you guys said, you consider these points. So -2, 5. -2 up 5 right here. Boop. -1, 2. You go where X is -1, and you go up to where Y is 2. X is 0 in the origin here. This point is called the origin in the middle. And then you go up to 1. And then you just continue that for the other side. And then what did you do?
You're gonna connect it.
And then you connected it so that you include all the other X values as input values. Otherwise, if I don't connect it, it affects the domain, right? So I want to include all the different X values I can plug in here. Like that. And what is that graph called? That's a parabola, yeah. We're gonna spend one whole day on the later on. Okay, so if I look at this graph, is it true that for every X value, I only get one Y value?
Yes.
For each X value, am I getting just one Y value?
Yeah.
Yeah, I'll do that on purpose, just to like, throw you off your game. Oh crap, wait, is it true? Yes. And so in this case, X, we're gonna think of X as an input and Y as the output. This describes a function. Okay, so this represents a function. And so now we're going to write it as f of x equals x squared plus 1. And again, some more notation here. So notice that here I'm writing it as an equation. Here I'm writing it in function notation. Okay. Here's some important things to take into account. F is the name of the function. So F is using that letter to say that's the function F. X is the input variable. And Y is the output variable. Okay. And so you'll see in math textbooks, you'll see this showing up a lot. Y equals f of x. And what that means is that the output values of your function are going to represent the y coordinates associated to the graph in the table. Okay. If on the homework you're being asked to label the parabola, do I label it with the letter F, Y, or X? Which letter represents the name of the function? F. So that's why they'll write the letter F next to the graph so that you understand that's the function that you're talking about. Okay. It's all things you've probably seen, but like I want you to know the purpose of it. Okay. Okay. You guys ready to get hella heavy with the algebra? All right. Stretch a little bit while I erase this next part. All right, now we did a lot of like conceptual notation stuff. Now we're going to jump a little bit into the algebra. That way we can work on that and answer any questions. You guys are asking good questions. If you know my needs work. All right. Okay. So something that's going to be a little bit challenging in this class, and when you get to calc, is that you're going to be given a function. And right now, we've been plugging in, like for example, this one, we've been plugging in numbers, right? We've been plugging in numbers. But it gets weird because later on, you're not going to just plug in numbers, you're going to plug in expressions, algebraic expressions into functions that represent a number. So let me show you what that looks like. So plugging, let's call it plugging in algebraic expressions into functions. Very abstract stuff that we're about to do, okay? So it's okay to feel a little uncomfortable. Let's do the first one here. So for the function, let's keep it with this one. For the function x squared plus 1, compute and simplify. And the homework will say something like this. Let's call this A. F of, you're going to plug in the expression a plus 1. And then B, instead, you're going to plug in another expression. Let's say it looks like this, negative x cubed. Very weird because we're not plugging in numbers, but the thing is that these expressions are representing something that represents a number. It's just in an abstract way. So before we jump in here, I want you guys to understand that F and a plus 1, they're not multiplying. I know that usually in math, we put two things together to represent multiplication. So this is not multiplication. So I'm going to write in red. Hopefully it shows up. So you wouldn't do something like this. you wouldn't distribute the F to give you like FA plus F. Okay, because it's not representing multiplication. And I'm showing you this because these are common mistakes that I see in when I'm teaching these classes. Question, yeah.
Could it just be like, if there was a number instead of F, we just plug that number to the previous?
No, you're gonna plug in this whole A plus one into the X. Is that what you meant?
Yeah.
Yeah,
Mhm.
okay. I'll do that in a little bit. I'm just
Okay.
showing you right now what you don't want to do.
Okay.
The other thing I see a lot is they rewrite the F with the function that it equals. They replace this F here and they write this times A plus one. That's another thing that I see. The brain kind of, I think, replaces the F with this. That's also wrong. Okay? What should really happen is what we did here. When I have a number and I'm plugging it in for X, you're replacing X with that number, right? So whatever I'm plugging into my function, it's going to replace the X. What is it that we're doing to X? What's the very first operation that's being done to X? Squaring it. So the way we write that is whatever I plug in, I put that in parentheses and I'm going to square that. But what is it that we're plugging into the function? A plus one. So then I replace that X with A plus one, but notice that I have to put it in parentheses. So that's notation you gotta be careful with. And then we're gonna add one to it. And so we're gonna expand this here, A plus one. Here's another common mistake that I see. I see this, I kind of distribute the square, and then I see this. Okay. That right there, that is called the freshman's dream. Apparently, because it's like, I wish I could do that. No, so that's incorrect. You can't just square these two things like that, because what this squaring means, it means that I'm getting A plus one and multiplying it with itself again. So I have to distribute, I have to FOIL it.
But isn't that what it equals?
Let's see. I'll leave it in red down here. Let's see. So A times A is A squared. A times one is A. It's all good. And then A times one is A. And then one times one is one. Is that it? Is that all I write on this side? Then, exactly, then I gotta bring this plus one comes from the multiplication, but this plus one is still needs to be there. Question.
Do you leave the parentheses around it?
You can go like that. Just to maybe visually see that that's what is separating this with the plus one, but you don't have to, because when you multiply it out, that's kind of the algebraic way of getting rid of the parentheses. Yeah, so notice that in reality, this is A squared. Let me write it over here. It's A squared plus 2A. And then what happens with these ones? 2. See, that's hella different, right? Because there's like 2A that shows up. It's all good. It's all good. Yeah, it's all good. It's all good. So in the homework, you'll be given a function and it'll tell you to compute and simplify. You're going to plug in that expression into the function and simplify combined like terms. This is what you would put into WebAssembly.
So we don't get the quadratic formula here?
No, that's later on when we're solving for stuff. Yeah, that's what we're solving. Any questions on this one? Right. Okay, here, instead of plugging in A plus one, it's still the same function. You guys see how it's still the same function because it still uses the letter F. So in this case, in parentheses, I'm squaring whatever I plug in, right? But what is it that we're plugging in? So in this case, it's negative x cubed and then plus one. So what do I do with these exponents here?
Do add them?
Add them or do I multiply them? Well, let's see. What am I multiplying with itself 2 times? So if it helps, just, just write it out. It's all good. So I'm doing that. I'm multiplying that with itself 2 times. So now what happens to those 3's?
No, now you're.
Now you add them in this case, which gives me 6. So in reality, these were supposed to multiply because I needed to get 6, right? What happens with the negative? I'm squaring it. So it becomes a positive. So it becomes positive x to the 6 plus 1. And then there's nothing to combine. So then that's it. This will be it.
Feels too simple.
It's the leap right here.
So when you multiply them, the exponents add, but then when you square them, they multiply.
If you have an exponent raised to an exponent, it multiplies.
Okay.
But if you have 2 of the same bases with the same exponent, then you add.
Okay.
Yeah. I think the shorthand is if an exponent is being raised to an exponent, you multiply. Yeah. Okay, I'm gonna give you guys 2 problems to try. Okay, they're gonna be a little nasty. All right. So again, compute and simplify, and then please check with your classmates, and then I'll go around and help you out. Okay, so we're going to use 2 different functions. So for number 1, use the function x squared minus 3x, and then I want you guys to compute f of x plus 2. So you're using that function and you're plugging in x plus 2 into it. Oh, before I see how here I used a. If I would have put x plus 1 here, I would have done the exact same thing, except I just used the x. Okay. Okay, this one's gonna be a little, I know you guys love fractions. So it's 1/2 pi r squared. And I want you guys to compute and simplify if you plugged in 3 over x plus 1 into that weird function. Right. Right. So let's spend some time on those. And then I think we'll take a break after this one. To here. Okay, I am seeing different results. So can I have you guys just stop real quick and just check with one another? See if you guys are on the right paths. Do a quick little check-in, quick little check-in. Yeah.
Yeah.
Like, if they just replace each X in that first.
Yeah, I
you're
just
gonna
realized
miss
that. So.
I think I did it right, but it was mandated, and I think they're already complicated.
Yeah.
I'm not. I didn't. But.
Yeah. Because if you find there's
The three squares, just replace the bars with that thing. At least you want to replace two things like. I don't know if you like just split up the top number and the bottom number. Or if you need to. I replace the bar. The R in the left side, use that R in the left side. So we should replace the R in the over there, these guys. I don't know. But I think this is. Yeah, I don't know. Oh, yeah, that's maybe it.
Okay, I stopped when you. Oh, no, I stopped.
Yeah, we're already kind of solid. That's like kind of.
Okay, guys, you can compare your work. Maybe your answer looks a little different.
That's the final.
about how to.
Actually, let me just write the rest here.
Oh, that's it. Negative.
9 5 over 2x squared plus 4.
Okay. So, two things. One, when the function shows the input variable multiple times, when you're plugging something in, you gotta make sure you plug it into wherever you see the input variable. So not just this guy, right? You gotta also plug it in here. Okay? Notice that here, for this one, R is the input variable. It only shows up once. Pi I threw there to kind of throw you off a little bit. Okay? But since R is the input variable, it's only being plugged in here, which is what this looks like. And then my other comment is, when you have a fraction that's being squared, you must square the top and you must square the bottom. Because remember, this really means you're multiplying 3x plus 1 times 3x plus 1 with itself. So it's really 3 being squared and the x plus 1 being squared. So then we get this. Now the question is, why in my answer, this is more of style, okay? That the textbook will be doing. Why for this one do I not expand it and I leave it x plus 1 squared, but for this one, I do expand it. Right? And because usually through the style of these textbooks, do you guys see how if I was to expand this, I was able to combine like terms and able to simplify it a little bit more? So here you do want to expand it because it'll help you combine like terms with the other expression. Versus here, if I expand it, I won't be combining like terms with anything else. It'll just be the same thing again. So it's okay to not expand it. It's also okay if you do expand it and distribute the two. That's also okay. Okay. What was saying, we'll read both of those correct. Here, a little bit of like, I guess fundamentals is you want to think of this as 1/2 pi. How can you write pi as a fraction?
Pi over 1.
Pi over 1. And then here I have a fraction 9 over x plus 1 squared. And so then you multiply all the numerators, gives me 9 pi. And I multiply all the denominators, and I wrote them next to each other to represent multiplication. Okay? So just some fundamentals with fractions to be careful with. Questions? Okay, let's go on a break. And then if you do have questions, I'll go and help you out. Otherwise, let's come back at 2:16. We'll resume at 2:16. Go for it, guys. Good job. I'll leave that up there. Can I move a little bit this way? Okay, and then you told me that
Yeah.
Emmanuel, okay, that's it. Sorry, guys, the video was, my recording was paused. I just unpaused it. So I'm gonna miss that part after the break till now, okay? Apologize for that. But you're here in person, it's all good. Careful with this one. Check with your classmates, please. I am seeing different answers. Yeah.
And that's. It seems to me maybe it's about. Yeah.
And so.
Like.
You guys can compare your answers here. So walking around, I saw this. Okay, let's talk about that real quick. If this is your answer, that means that on your graph, all the X values from -2 to +5 are being used. Is that true? No, because if you look here, the graph does not use any X values between 1 and 2. So you need to somehow show that. So that's why I can't just put the -2 and the 5, because this assumes I can use the X values 1.1, 1.2, 1.3 when they don't associate anywhere in the graph. So what you're gonna have to do is you're gonna have to split it into 2 intervals. You would say this part of the graph uses X values from -2 to 1. Is 1 included? Yes, because it's a closed dot. And then you have to make another interval to say this part of the graph uses X values between what and what? 2 and 5. Does it include the 2? No, that's why there's an open circle. Does it include the 5? Yes. And what did we say Monday? When I want to include 2 intervals, you say U for or. Yeah, be careful.
You're marrying the two equations.
Yeah, exactly. So it's so this is saying your input values are anything in between -2 and 1, including them, or 2 to 5, including the 5. So that's what you read this for. Okay, Y values. What's the lowest bound Y value? What's like the smallest Y value that we seem to be getting to? -3. Do I include it? No, right? That Y value is not included. Is it included anywhere else? Not at all, right? So yes, it's totally not included. What's the highest Y value you see? Oh, what did I say? That's supposed to be 4. Sorry, 4 right here. So if I put a 4 though, and it's included, is it true that I am using all the y values in between -3 and 4?
Yeah.
Let's see. So everything -3, and then if this is all these y values are being used, right? Is 0 being used? Yes. It is being used. It's being used at what is the y value of this point? What's the y value at that point? So it's being used. It's part of the range. What about anything after 0? Not here, right? But it is here. It is being used. So there actually is no jump of intervals for the range. This is the range. Yeah, so just because you see the graph being detached, it doesn't, you can't assume that there'll just be split intervals everywhere. You really have to look at the values being used. Questions?
Shouldn't it be the other way around?
It should not, no, because remember, intervals need to go in an increasing order.
Oh, it's got.
Yes, yep, no, that's a good question. Yeah, so you don't want to write, it like this. That would be wrong.
Do you write it wrong? This one is wrong.
I'll give you some points for you understanding that you're kind of going between 3 and 4, -3 and 4. It's just you need to know that it's increasing more. Like you're like 95% there. Yeah. Okay. So this is the thinking behind finding domain and ranges of graphs and functions. Okay. The last thing we're gonna do is more algebraic. We're gonna have to leave it 3:10-ish. Or not, we'll see. Okay, so for this one is finding domains algebraically. So let me start with an example. Actually, let's do both. Yeah, because we're not gonna have time for the practice one. Let's do both. So let's say I need to find the domain of, and number 1, the function is going to look like this. Square root of 5 minus x. And over here, the function, let's call it g, little g, is 1 over x minus 2. Okay. So going back to what I was saying here, possible. What are all the possible input values? That's going to be very key for the algebra part. Okay. When you're dealing with this algebraically, you want to avoid negatives. Let me actually write the word avoid. Avoid negatives inside square roots and avoid 0 in the denominator. We talked about on Monday, when we had negatives inside the square root, what kind of numbers were that? What was that giving you? We're giving you imaginary numbers, right? We weren't looking at functions at all, though. We were just looking at numbers. When it comes to functions in our classes and at DVC in general, you're not going to use imaginary numbers for functions. Okay, so they're not going to be defined. So we're not using imaginary, so we don't want negatives inside the square root. Okay. So that means that when you're looking at this function, I have a square root. I don't want negatives inside the square root. So give me, for example, a number that we cannot plug in. If I plug in 4, let's see, what's 5 minus 4? That's 1. That's cool.
5.
6. If I plug in 6, what's 5 minus 6? That I can't do. So if I try to plug this in a 6 into the function, what's going to happen is that we would say that it's undefined. So 6 is not a possible input value because it spits out something that's undefined. So our domain does not include the 6. So the task here is I have to find all the X values that I can plug in, so I do not get a negative. So if I don't want this expression to be negative, what do I want it to be? Or zero. So that means that the reason this is hard for students is because you have to introduce math here yourself. I need this to be positive or zero. How do I write that mathematically? How do I write that I want 5 minus x to be positive or zero?
Greater than or equal to 0.
You introduce an inequality. So you need to solve this inequality here. By solving this inequality, it's going to tell you the X values that will guarantee you to get a positive or a zero in there. Let's see if that's true. So what would you guys do here to start solving for X? Minus the 5. This cancels out. I get negative X. I get minus 5. And then here, be careful. What do we do to get rid of the negative?
Divide by -1.
You want to think of this as -1 times X, right? So you're going to divide the -1. What happens when you divide or multiply by a negative when you're solving an inequality? You got to swap the inequality whenever you multiply or divide. So that means that these cancel, but because I divided by a negative, I got to flip the inequality. And then this becomes 5. By solving this inequality, it now tells me which X values will be in my domain. Anything that's what? Less than or equal to 5. Was 6 less than or equal to 5? No, which is why it failed. When you do the domain, you're going to have to use interval notation. So you got to do what we did on Monday. On interval notation, what's the smallest X value? Let's see. Hold on. Here's 5. X is less than 5. So remember, I was having you guys write it like this because it does not include the 5, right? So it's anything less than 5 and not including 5. So here's where we're practicing what we did on Monday. So let me repeat it again. What's the smallest X value? There is none, so we put negative infinity. What's the biggest X value? But, oh, I was wrong. Should be a square bracket. Because there's an equal, it does include it. Sorry about that. And so when you guys see a square root in your function and you're being asked to find the domain, that's where you want to get to. That thinking is, I don't want a negative. So you're going to have to set whatever's inside the square root and make it an inequality greater than or equal to 0.
And
Question.
you said that when you divide by a negative, the inequality flips?
When you're solving an inequality, yes, you flip the inequality. So here's one of those examples you could refer back to the recording to. Okay. So that's what you're going to do when you're dealing with square roots. Here's the other thing you don't want, because it gives you something undefined. We can't divide by 0. Okay. So that means that when I plug in an X value here, I don't want the bottom to be 0. So this one's a little bit easier. What X value can we not plug in? 2, because then that would give you 0, right? It's not that you exclude X equals 0. There's a difference between excluding X equals 0 and excluding the X value that makes the denominator 0. Right? 2 is that number that you don't want. So in this case, if this was a more complicated expression down here, like let's say a nasty quadratic, that it's not that easy, what you do is you say, okay, well, I don't want this to be equal to 0, and then you solve for X. Right? And so I add the 2, and so automatically here it tells me I don't want X to be 2. And that you exclude. So on a number line, let's see what that looks like on a number line. Whoa. How do I write I don't want X to be 2 in interval notation? Yeah.
Wait.
Circle, arrow, yeah, so in a previous math class, you probably covered it like that, right? The way the textbook's using it here, it says. Kind of like this weird crap like this. Like anything less than 2, but not including it, and anything greater than 2, but not including it. So what does that mean? 1 interval or 2 intervals? 2 intervals. So you're gonna say 1 interval for everything less than 2. So there's nothing that's the smallest, so it's negative infinity. Up to 2, but you don't include it. That's the left part.
Do we say or in here?
And you do say or, yeah. Union, or everything that's greater than 2. So for this interval, for this one, what's the smallest x value? 2, but you don't include it. Yeah, and then it goes up to infinity. So in this case, you would do a union because it's 2 intervals, yeah. On the homework, they might give you a quadratic down here. You solve the quadratic. Somebody asked me, where do I use the quadratic formula? Here's where it might show up. You solve a quadratic, and let's say on the quadratic, it told you, do not include 2 and do not include 5. So then, how many jumps do you have to make? You'd have to make 2 jumps. Everything less than 2, everything in between 2 and 5, and everything 5 and greater.
How would we write this in between?
So yeah, actually, hold on, before we leave. You guys seem very eager on that one, so hold on, ultra mode. Okay, so let's say, here's third example, let's say it was something like this. Let's say it was something like that. You don't want to plug in 2, because that'll make this 0, which makes the whole thing 0 or 5. So you can't have x be 2, and you can't have x be 5. So on a number line, here's 2, here's 5. You have these holes here that you don't want to include. So you're going to need an interval for everything less than 2. Just like this one. So it would be negative infinity. Well, we can't draw infinity. To 2. Everything in between 2 and 5 is good though. So don't forget that part, otherwise you get it wrong. So everything in between 2 and 5, and then everything 5 and greater. So you get 3 intervals. What do you put in between each of these? You put a big fat U. So in this case, you're going to use 3 units. Okay. So the more x values you have to exclude, the nastier the interval. Right? Okay, that's good timing. Okay, so hold on, let me just clean up real quick, and then we're gonna walk to the Math and Engineering Student Center. Good job, guys.